Hello, welcome to Meki Techie. Learn as engineer, teach as a champion. First of all, I would like to thank my family for their continuous support and encouragement for creating these kinds of technical videos in the public domain. And I would like to thank my mentor, Professor R. Surendran from Government College of Technology, Coimbatore, for igniting me a spark of creating these kinds of technical videos in the public domain. And I would like to thank Almighty, my God, for my good health and broad mind. And I would like to thank my friends, followers, my dear students, and subscribers for their continuous support and encouragement for creating these kinds of videos. Today's topic of interest is crystal structure. In the materials science, the crystal structure will play a major role, and this crystal structure is difficult to understand. But I am going to give you a beautiful way of understanding and remembering these material science crystal structures. So, with this, the background, the crystal structure, which is everywhere in every metal, when we attention in detail, or we can zoom in 100x zooming, we can easily visualize the crystal structure of the different material. So, in the crystal structure, we have to notice the following things. That is, the value of suspectability is very important. The value of suspectability, which is in the form of three phases, one is diamagnetic, another one is a paramagnetic, and ferromagnetic. In the diamagnetic, it is a small and negative suspectability is there, and paramagnetic, a small and positive suspectability is there, and ferromagnetic is a large and positive suspectability are there. Here, if we start the material science, we have to notice that the amorphous, mesomorphous, and crystalline structures. The amorphous is the atoms are arranged stochastically, that is granular atoms, which is called as an amorphous materials. That is, the formation is irregular form. The best example of the amorphous metals is glass, where mica it is called as a mesomorphous material, which is the mesomorphous is it is irregular in some of the directions but not in the other direction. One direction is arranged property, so that is one direction arranged property, that is called as a mesomorphous. The mica is the very good example of the mesomorphous, where the crystallines or atoms are arranged in definite and orderized manner. So that is why the crystalline structures, the most of the materials having crystalline structures, that is the atoms are well organized, well arranged, and it is having definite place. So that is why the materials are called as a crystalline materials. Here, in the crystalline materials, we have to notice the four different properties, that is isotropic, anisotropic, orthotrophic, and viscoelastic. Here, first of all, isotropic is the property of the material, the same elastic property in all direction. The property of the material which contains same elastic property in all direction, which is called as an isotropic materials. In the isotropic materials, the total number of elastic constants are only four. That is your Young's modulus, bulk modulus, rigidity modulus, and Poisson ratio are those four. In this, if we notice the any two elastic independent constant, any two elastic constants, the other two can easily find. Therefore, we know that the relationship between E is equal to 3k into 1 minus 2 mu, and E is equal to 2c into 1 plus mu. So this is the equation. If we know the E and mu, then we can found C and K. So either you can get, if you can know E and K, we can easily find mu and C. So with this information, this is called as an isotrophic material. And all the engineering applications, we assume our material is in the form of isotrophic. But in the case, if it is not well defined crystalline structure, it won't be seen as an isotrophic. Then anisotrophic is the different elastic property in different directions. So that is called as anisotrophic. Most of the composites are in the form of either anisotrophic or orthotrophic. For a description of an anisotrophic, we need a 21 elastic constants. We need a 21 elastic constants like E, G, K and mu. Whereas for the orthotrophic, we need a 9 elastic constants. We need a 9 elastic constants for orthotrophic. Sorry, here it is mistaken. It is 9 elastic constants. The ortho means 90 degree. Ortho means 90 degree. That is, elastic property in mutually perpendicular directions are same. That is called as an orthotrophic. And next one is the viscoelastic. Viscoelastic is the non-crystalline organic polymer. This is called as a non-crystalline organic polymer. It is a time bounded behavior. It give a time bounded behavior. Here, as I said earlier, the low carbon steel is the mild steel, medium carbon steel is the plain carbon steel, which is used for shaft axle, screws, connecting rods, and truck axles, etc. And high carbon steel, which is used for the screwdrivers, rail vanes, wheel beams, and chisels, are manufactured using high carbon steel. Here we are going to see a different structure. Nearly we have a 5 different structures that we have to understand very nicely in this figure. So here, please turn your video. Here the structures are SC, simple cubic, BCC, body center cubic, FCC, face center cubic, HCP, hexagonally closed packed, and a diamond structure. Here the number of atoms or effective number. For SC it is 1, BCC it is 2, and FCC it is 4, HCP it is 6, and diamond it is 8. Next, atomic packing factor. For SC it is 52 percentage, and BCC it is 68 percentage, and FCC it is 74 percentage, and HCP is 74, and diamond is 34 percentage. And percentage of empty, the percentage of voids is 1 minus atomic packing factor, APF. That is, if the 1 minus 0.52, it will come 0.48. That is 48 percentage of voids present in SC, and 32 percentage of voids present in BC, and 28 percentage of voids present in FC and HCP. And the next one is the coordination number. The coordination number for SC it is 6, and BCC it is 8, and FCC it is 12, and HCP it is 12, and the diamond structure it is 4, where the relation between A and R, atomic size and radius, is for SC it is 2R is equal to A, and for BCC it is 4R is equal to root 3 times of A, and FCC it is 4R is equal to root 2 of A, and HCP it is 2R is equal to A, and diamond structure 8R is equal to root 3A. And the slip system for SC is 6, BCC is 48, and FCC is 12, and HCP is 3. And theta and theta, which is the angle. For SC it is 0 and BCC it is 30 and FCC it is 45 and HCP is again uh, 0 degree and diamond is not found. And here I would like to give a crystal structures, different types of a crystal structures which are available. The crystal structures like cubic, tetragonal, orthorhombic, rhombohedral and hexagonal and interaxial lengths and interaxial angles have mentioned here. For the cubic, the interaxial length is A is equal to B is equal to C and the angles alpha is equal to beta is equal to gamma, which is equal to 90 degree. The next tetragonal, the A is equal to B but not is equal to C and the angles are alpha, beta, gamma, which both are equal to 90 degree. In orthorhombic, A is not equal to B and not equal to C, where alpha is equal to beta, which is equal to gamma, which is equal to 90 degree. And rhombohedral or triagonal, that is A is equal to B is equal to C, and alpha is equal to beta is equal to gamma, which is not equal to 90 degree. And hexagonal, the A is equal to B, not is equal to C, and alpha is equal to beta is equal to 90 degree and gamma is 120 degree. And the other structures monoclinic, that is alpha equal to beta, alpha not equal to B, A is not equal to B, not equal to C, alpha equal to beta equal to gamma, which is not equal to 90 degree. This you have to understand. And next, triclinic. Triclinic is A is not equal to B, which is not equal to C, where alpha is not equal to beta, which is not equal to 90 degree, but gamma is in 90 degree. And here the number of independent elastic constants for the different structures are given here. For the isotrophic, which is 2, anisotrophic or orthorhombic it is 21, triclinic or orthotrophic it is 9, cubic which is 3, hexagonal which is 5, tetragonal is 6, and monoclinic is the 13 independent elastic constant is required for monoclinic. Next, we are going to see the different form of the different materials in the crystal structure. In the simple cubic, fluorspar, polonium, manganese, and manganese are in the form of SE structures, and amorphous charcoal and glass are in the amorphous structure. BCC, alpha iron, sodium, potassium, vanadium, tungsten, niobium, molybdenum, thorium, barium, and ferrous materials are in the form of BCC structure. And FCC structures are silver, aluminum, gold, platinum, gamma iron, lead, copper, cadmium, nickel, thorium are in the FCC structure. And for the HCP structure, titanium, cadmium, zinc, manganese, beryllium, germanium, all are HCP structures. That is helium, beryllium, cadmium, graphite, titanium, cobalt, zinc, magnesium, alpha titanium, all are in the form of HCP structures. Next, the metalloids means the carbon, phosphorus, silicon, sulfur, all are called as a metalloids. And here I will found a beautiful equation, the average number of grains. The average number of grains n is equal to 2 power n minus 1, where n is the size of the grain or size number. That if we know the size number, we can found number of grains present in the system. So with this information I am going to close the session. I hope that you can enjoy the session. I am giving enough detail about the crystal structure. Thank you all.